Chapter 15 is on conditional probabilities. First, we're going to review a little bit from Chapter 14. We are going to start with an example where we have a spinner that has 4 equal sections. The sections are red, blue, green, and yellow, and we want to find each probability given 2 spins. So go through each one of these and see if you can do them without my help. Pause until you're ready to go through the answers. Number 1, we want first a blue, then we want a blue the second time. The probability of blue is 1 out of 4. The probability of blue again is 1 out of 4, and you want both of those to happen, so you're multiplying. 1/4 times 1/4 is 1/16. Number 2, the probability of not getting yellow is 3/4. The probability of getting green is 1/4, and you want both of these events to occur, so you're multiplying. 3/4 times 1/4 is 3/16. The probability of at least 1 green, remember at least we go backwards to work out that answer. We do 1 minus the opposite of this situation. 1 minus the opposite of this situation would be no greens, so 1 minus 3/4 times 3/4, which would be 1 minus 9/16. 7/16 is our final answer. The probability of neither spin being red is 3/4 times 3/4. That's 9/16. Okay, now we get into conditional probabilities. These are occurring when we have dependent events. 2 events are dependent if knowing the outcome of one alters the outcome of another. A conditional probability contains the condition that limits the sample space for the event. The probability of B line A means the probability of event B given line A. Given event A, that line stands for given. The one to the right of it, the A in this case, is the one that's given. Okay, here's the formula for conditional probability. The probability of B given A is the probability of B and A over the probability of just A. In other words, the probability of both divided by the probability of the given. Here's our example. Of all the snowfalls in Buffalo, New York, 5% are heavy. If a heavy snowfall occurs, schools close 67% of the time. After a light snowfall, schools closed only 3% of the time. There are 4 probabilities we're going to find, and we're going to take them one at a time on each of the next 4 slides. Starting with the first one, the probability that school is open given it was a light snowfall. Okay, here's a tree diagram in this situation. We're going to fill in this tree diagram, and it's very helpful for some conditional probabilities. This is an example of a problem where we'd want to use a tree diagram. We start with whether it was a light snowfall or a heavy snowfall, and then from there we go on to the idea of whether school is open or school is closed. Now the first thing they told us was there was a heavy snowfall 5% of the time. That means the other 95% of the time it was a light snowfall. Now they said if it was a heavy snowfall, schools closed 67% of the time, which means that 33% of the time it was still open if it was a heavy snowfall. If it was a light snowfall, they told us school was closed 3% of the time, which means 97% of the time school's open if it were a light snowfall. Okay, so we got our probabilities filled in our tree diagram, and the question is asking us to find the probability that school is open given it was a light snowfall. The formula tells us we do the probability of both events occurring divided by the probability of the given. Both events occurring mean the probability of it being light and open divided by the probability of the given, which is that it's light. We're focusing on the top part of our tree diagram, the part that I've circled in here. The probability of it being light and open means the probability of 0.95 times 0.97. That's the top of the fraction. That's both events occurring. Divided by the probability of it being light, which is 0.95. Now, go ahead and multiply and then divide. You get 0.97 or 97% for a final answer. Number 2 asked us to find the probability that school is closed given that it was a heavy snowfall. We're focusing on the bottom part of our tree diagram, and the formula tells us that we do the probability of both events, heavy and closed, divided by the probability of the given, which is the heavy snowfall. The probability of both events occurring is the probability of 0.05 times 0.67, that's the top of the fraction, divided by the probability of the given, which is the heavy snowfall. 0.05 goes on the bottom of the fraction. Multiply and divide. 0.67 or 67% is our final answer. Number 3 asked us to find the probability that school is open. This can occur in one of two ways. We're going to focus on the top part of our tree diagram and the middle of our tree diagram, both paths to which the school could be left open. On the first path, we're doing 0.95 multiplied by 0.97. On the second path, we're doing 0.05 multiplied by 0.33. Take each path, and then when you're done multiplying, you add them up. Because you're saying it could happen in the first path, or it could happen in the second path. You should end up with a probability of 0.938 or 93.8% chance that school is going to be left open. Question 4 asked us to find the probability of a light snowfall given that school was open. We're going to start with the formula that says the probability of both on the top of the fraction, divide the probability by the given, which is open. The probability of it being light and open is the top part of our tree diagram. That's 0.95 times 0.97. The probability of it being open would be one of the two paths that we have in which school is left open. So on the bottom of the fraction, you're going to have each path multiplied and then added up. Top of the fraction, 0.95 times 0.97. That's both light and open. Over the probability of school being left open, which is the 0.95 times 0.97 path, the 0.05 times 0.33 path, and then those two paths added up. Multiply, and then divide. You should get a 0.982 or 98.2% chance. Okay, here's another one to practice. We're drawing a card at random from a standard deck of cards. We want to find the probability of a heart given that the card was red. That line means given. So the probability of being a heart and red is 13 cards, added the probability of being just red, which is 26 cards. So 13 out of 26 is a half for a probability. Number 2, the probability of being a red given that it was a heart. The probability of being a red and a heart is 13 cards out of the deck, and the probability of being just a heart is 13. So 13 over 13 is 1 or 100% chance. Number 3, the probability of being an ace given that it was red. The probability of being a red ace is 2 cards out of the probability of being an ace. The probability of being a red, which is 26 cards. 2 out of 26 is 1 out of 13. And then number 4, the probability of being a queen given that it was a face card. You're going to do the probability of both a queen and a face card, which is 4 queens that are face cards, out of the probability of being just the face cards, which there's 12 face cards in the deck. That's all the jacks, queens, and kings. There's 12 total in the deck. So 4 out of 12, which equals 1 out of 3. Here's another one to try. In this situation, we're looking at the probabilities of whether or not you have high blood pressure and the probability of whether you have high cholesterol or not. Okay, so number 1 says we're going to find the probability of having both conditions. That means you have high blood pressure and high cholesterol. That's the 0.11% chance, the 11% chance in the top left corner of our chart. Both high blood pressure and high cholesterol. Number 2, we want to find the probability of having high blood pressure. Look all the way down to the total of the percentage of chance of having high blood pressure, which is 27% chance, or 0.27. Number 3, we get into some conditional probabilities. A man has high blood pressure. That's going to be given to us. We want to find the probability that he has high cholesterol as well. So you're going to do the probability of both conditions, high blood pressure and high cholesterol, which is 0.11, divided by the probability of the given, which the given is that he had high blood pressure. So we're dividing by 0.27. 0.11 divided by 0.27 is 0.407, or 40.7% chance of this happening. Number 4, the probability of a man with okay cholesterol has high blood pressure. So it's given that he has okay cholesterol, and we want to find the probability that he also has high blood pressure. The probability of both okay cholesterol and high blood pressure is 0.16, and we're dividing that by the given, which is that he had okay cholesterol. That's a 0.68. If you divide 0.16 by 0.68, we get 0.235, or 23.5%. Here's another example. We have a box in our room that contains old batteries. It has a dozen old batteries in it. 5 of them are dead, 7 of them are good. We want to start picking out batteries one at a time and testing them, and we're not going to replace the batteries. So first we find the probability that the first two that we choose are both good. Well, the first one you choose has a 7 out of 12 chance of being good. The second one has a 6 out of 11 chance of being good. 6 because there's 6 good ones left out of 11 because there's 11 total batteries left. So 7 out of 12 times 6 out of 11. So it would be 7 out of 22 total for the probability. Number 2, find the probability that at least one of the first 3 works. This is an at least problem. We go backwards and do 1 minus the opposite of the situation, which the opposite of the situation would be that none of the first 3 that we choose work. So 1 minus the probability that none of the first 3 work. That would be 1 minus 5 out of 12, meaning the first one is not working, times 4 out of 11, meaning the second one's not working, times 3 out of 10, meaning the third one's not working. We're subtracting one bad one off each time and one total battery off each time because we're not replacing them. Type this in your calculator. You should end up with 21 over 22 in fraction form. Number 3, find the probability that the first 4 we pick all work. The first one has to work, the second one, the third one, and the fourth one. The first probability is 7 out of 12. The next one would be 6 out of 11. The third one is 5 out of 10. And the fourth one is 4 out of 9. Multiply these in your calculator. You should end up with 7 over 99 in fraction form. And number 4, find the probability that you have to pick 5 batteries in order to find one that works. That means the first 4 were all bad, and then the 5th one was the good one. So starting with the first 4 being all bad, that's 5 out of 12 times 4 out of 11 times 3 out of 10 times 2 out of 9. And then for the last battery, when we multiply, we still have 7 good ones left out of 8 total batteries, so times 7 out of 8. Multiply these in your calculator. You should end up with 7 over 792 in fraction form. Testing for independent events. Two events are independent if the probability of one under the given condition of the other is the same as that probability whether you knew the condition or not. Okay? In other words, the probability of B given A is still the same probability as B by itself. Knowing the outcome of A does not affect the outcome of B. That makes them independent events. Here's our example. We're going to draw a card from a standard deck. Is the probability of getting an ace independent of knowing the suit? Meaning, is the probability affected whether we know the suit or not? First, we're going to test the probability of getting an ace, and then we're going to compare that to the probability of getting an ace, given that we knew it was a certain suit, for example, given that we knew it's a club. The probability of getting an ace is 4 aces out of 52 cards, which reduces to 1 out of 13. There's 1 ace in every 13 cards. Now let's say we knew it was a club. Well, there's 1 ace in all the 13 clubs, so that's still a probability of 1 out of 13. Those probabilities are the same whether we knew it was a club or not. It didn't affect it. Since the probabilities are equal, the probability of getting an ace is independent of knowing the suit, meaning it's not affected whether you know the suit. The probabilities did not change.